Hello everyone, welcome back to my general chemistry mini lecture. Today we'll talk about the element atoms and we will talk about how to draw the electrons configuration of the atom. Okay, first we'll talk about the definition of element. Based on IUPAC, that's International Union of Pure and Applied Chemistry, an element could be a species of atoms, and all atoms with the same numbers of protons in the atomic nucleus. Another definition of the element is a pure chemical substance composed of atoms with the same number of protons in the atomic nucleus. We talk about the periodic table in most of the chemistry class, right? So the periodic table of elements is an organization of the elements according to the atomic number, which is also the number of protons in the nucleus. So that's the hydrogen, the number 1, and that is called the atomic number. So, and carbon, number 6. So the 6 is atomic number. That is the protons number in the nucleus. And this is the symbol of the element, carbon. And this number under the symbol is called atomic mass. It's also molar mass. This is a very important number because you need this to calculate the molar mass of a compound and for the mole calculation, and use a lot in the stoichiometry calculation. Okay, so, and you can see the number above each column is the group number. Okay, we have two type of group. A group is called a main group or representative group, and the B group is called a transition elements. Okay, and we see the colors are different. This teal color is the metals, and yellow is non-metal. There's one non-metal here. So you can see majority is metal, and non-metal is the upright corner here, and the pink colored is metalloid. That's half metal, half non-metal. Sometimes it's called a semi-metal, or you can say semiconductors. The most famous semiconductor is silicon. That is a basic building material for CPUs. Okay. What's atom? By the IUPAC definition, atom is the smallest particle which is still characterizing a chemical element. So we cannot just say atom is the smallest particle. No, okay, you have to follow the definition. It's still characterizing a chemical element. Okay, so the atom consists of a nucleus of a positive charge that comes from the proton. Okay, so usually we use Z, it shows the proton's number. That is also atomic number, okay, in the periodic table, and carrying almost all its mass in the nucleus. Okay, and more than 99.9% of mass is on nucleus of the atom, and there are Z electrons. The number of electrons equals the proton's number. Okay, that determines its size. Okay, so although more than 99.9% of mass is on the nucleus, but the nucleus is very, very small. If the size of the atom is like the size of a classroom, then the size of the nucleus will be the size of a dust. Almost nothing. But the mass, it's all on the nucleus, basically. Electrons has very, very little mass. Okay, so sometimes we see those symbols. Let's see the meaning of those symbols. If you see this C, that means it is a carbon element. It's a non-metal, or it's one carbon atom. You can say that. So you have to see the context. Okay, now Ba, it's another element, barium. Barium is a metal, or you can say it's one baryon atom. This is oxygen element, it's a nonmetal, or you can say it's one oxygen atom. This is oxygen molecule, okay? So it's a free element, it's a molecule. See, we call this diatomic molecule. Sometimes just called oxygen gas because it's gas. It's a type of free element of oxygen. This is phosphorus. It's a free element. It's also a molecule. Okay, so it's called a polyatomic molecule, phosphorus. This is another polyatomic molecule. That is a sulfur. It's a free element. It's a molecule of sulfur. Okay, now let's look at the isotopes. So this is the hydrogen element. See, this shows 3 different atoms of hydrogen. So one element could have different atoms with different nucleus. So, but they must have the same number of protons. See, this is the hydrogen 1, hydrogen 2, this is hydrogen 2, this is hydrogen 3. That number is the mass number. Mass number equals the protons number plus neutrons number. This is proton. And in this first isotope of hydrogen, actually there's no neutron in the nucleus. So the mass number is just 1. And you can also write mass number here, protons number here. This is electron. So this is the major isotope of hydrogen. And this is another isotope of a hydrogen element. So there's 1 proton and 1 neutron in the nucleus of this isotope. So the mass number is 2. 1 plus 1 is 2. The proton number is still same, 1. Okay, so you can see 2 is mass number here. But there's still 1 electron because the electron's number is the same as the proton's number. This is the other isotope of hydrogen, hydrogen 3. We have 1 proton and 2 neutrons in the nucleus. So that's mass number is 1 plus 2 is 3. And, oh, sorry, that's a typo here. This should be 3, okay? And this is the electron's number, same as proton, okay? So isotope, they are the different atoms of same element. Example here, carbon. Carbon, actually, there are 3 isotopes, carbon 12, 13, 14. Okay, and oxygen has 3 isotopes, oxygen 16, 17, 18. You can see they all have the same protons number but a different mass number. Same protons number but different mass number. Another example, copper. There are 2 isotopes, same protons number 29, but they have different mass number 63, 65. Okay. Now let's talk about the electrons' behavior. Based on the modern theory, it's called quantum mechanics, the electrons' behavior is not random, okay? So they are not like a satellite, also not like anything we can imagine, actually, based on the quantum mechanics. The electrons, they will only be observed in some area called atomic orbital. And you cannot for sure see where is that. You can only know they have a higher probability to be observed in that area, that 3D space area. It's called an atomic orbital. This shows the electrons number and the protons number again. So hydrogen, there's just one electron. For carbon, there are 6 protons, so there are 6 electrons outside. So if there are more electrons, the structures or configuration will be more complicated. So we'll see the second orbitals first. Okay, so the energy are different of those different orbitals. See, this is 1s orbital, this is 2s orbital, that's a 3,2p orbital. The 3,2p orbitals actually called subshell. So we can call this 2p subshell. In a 2p subshell, there are 3 orbitals. 3p orbitals. And the shape of s orbital is like spherical, and the p orbital is like dumbbells. Okay, so that's again s orbital, that's p orbital, that's in 3p subshell, and that's 4s 3d subshell. There are 5 orbitals. In the 4p, there are 3 orbitals again. That's 4p subshell. 4d subshell, there are 5 orbitals. And the 4f, there are 7 orbitals. That in the 4f subshell, there are 7 orbitals. There's a rule. So in each atomic orbital, the maximum number of electrons is 2. So in the 1s orbital, you can also say 1s subshell, maximum number is 2. 2s, also 2. 2p subshell, they could have up to 6 electrons because there are 3 orbitals. 3s, 2. 3p, 6. 3d, 10, because there are 5 orbitals. Each orbital could have up to 2 electrons in there. So there are 10 as maximum number of electrons possible in the 3d subshell. In the 4d subshell, also 10, but in 4f subshell, maximum number of electrons is 14. This shows the shape of a d orbital. It could be like a shamrock or like a pacifiers. The energy level shown here. So also you can write this in order from lowest energy to higher energy. And there's a rule. If you have electrons filling those atomic orbital, they have to go to the lowest orbital first. When a lower orbital fully filled, they will go to the higher atomic orbitals. So then when they are full, and they have to go to the higher. So they have to fill the lowest first, and then slowly go into the higher. Okay, let's see some examples. Keep that in mind. We just talked about the energy level here, okay? And the maximum number of electrons in each subshell is in S subshell 2 maximum, P 6 maximum electrons. D, it could have up to 10 electrons in a D subshell. In F, they could have up to 14. I have 4 examples shown here. Magnesium. Before you can write the electrons configuration, you have to know how many electrons in the atom. So, and that number equals the protons number. Magnesium, atomic number is 12. So there are 12 electrons. So that 12 electrons, first 2 electrons go to the lowest 1s. See, this 1s is the subshell, and this 2 is the electrons in this subshell. Then 2s2. In the 2s subshell, you have 2 electrons filled. We used 4, so we have 8 more electrons have to go to the higher. So that will go to 2p, right? This is order. You have to go to 1s first, and then 2s, then 2p. 2p could have up to 6 electrons. And now we used 10 electrons. We still have 2 left. So that must go to 3s, because now 2p is already maximum. 3s2, that's it. So because s could have 2 electrons, now all electrons go to the corresponding atomic orbitals or subshells. Now look at the bromine. Bromine, there are 35 electrons because the atomic number of bromine is 35. Now follow the same order. 2 electrons go to 1s, 2 electrons go to 2s, and 6 electrons to go to 2p, and then 2 electrons go to 3s, and then 6 electrons go to 3p. You have to keep an eye on the electrons. Okay, now currently we used 18 electrons. 2 plus 2 plus 6 plus 2 plus 6, 18. Now keep going. After 3p is 4s. 2 electrons in 4s. And then we still have more electrons. Go to 3d, 10. And then we used 30 actually. So we still have 5 electrons. So that will go to the 4p5. So because after 3d is 4p. So this is important energy order. And that's it. That's it, the electron configuration of a bromine. Copper have 29 electrons. And then follow the same procedure 1s2, that's the electron number, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. So now we use all the 29 electrons, and you can double check. Add these electrons number together, should be 29. Copper will actually not have this electron configuration because there's another rule. If the electron can fully fill the subshell or half fill the subshell, that will be more stable. So since the 3d9 just need one more electron to be fully filled, so they will actually borrow one electron from 4s. Or you can say one of the 4s electron will jump to the 3d to form 3d10, and then 4s just have one electron. This configuration will be more stable because this fully filled d subshell. Another example is chromium. Chromium has 24 electrons. Atomic number is 24. And then follow the same procedure, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. 3d4 is need one more electron to be half filled because 3d subshell, there are 5 orbitals. You have 4 electrons. One of the orbital is empty. So if you can borrow one electron from 4s, you can form 4s1, 3d5. This is more stable than this original arrangement. So this will be the real electron configuration of chromium. Okay. There's a way to write a shorthand. It's called a noble gas shorthand configuration. So for example, we know helium, there are 2 electrons. So helium's electron configuration is 1s2. That's it. It's a noble gas. And so if you have a carbon, there are 6 electrons. The electron configuration, right, 1s2, 2s2, 2p2. We can use the helium as a symbol to represent, this is called inside or core electrons. And this second shells electron will be still shown here. So, and for oxygen, same idea. There are 8 electrons, and so you can write this configuration as this 1s2, 2s2, 2p4. You can use helium to replace this core electrons 1s2 because that is the same as the electron configuration of the helium. So this is the noble gas shorthand notation. Neon electrons configuration is 1s2, 2s2, 2p6. That's another noble gas. So sodium, there are 11 electrons. That is the sodium's electrons configuration. You can see the core electrons here can be replaced by neon in bracket. So only shows outermost shell's electron. Chlorine, there are 17 electrons. This is the complete electron configuration, but we can use neon replace this core electrons because it's the same thing as neon. So neon in bracket 3s2, 3p5. So that's the noble gas core shorthand notation of chlorine. Same thing, krypton. There are 36 electrons. That is electron configuration of the krypton. And strontium, the electrons configuration, if you write all of them, complete is like here. But actually you can see the core electron can be here. So this can be replaced by the krypton. So you can write this as much shorter notation of the electron configuration using the krypton as the noble gas to represent the core electrons and 5s2. So those outermost electrons called valence electrons. Okay, it's very important when we write those Lewis structures, and because they are those electrons involved in forming chemical bond. Okay, this is all I want to talk about the structures of the atoms, electrons configuration. If you have any questions, please let me know. Okay, good luck.